I'm Gayatri. In this video, I'm going to explain about classification and regression trees. So, coming to CAR, which is in short for classification and regression trees, is a machine learning algorithm that constructs decision trees for both classification and regression tasks. It operates by recursively partitioning the input space based on feature values, with each partition associated with a specific prediction or outcome. This process continues until a stopping criteria is met, resulting in a tree structure where each leaf node represents a predicted class or value. CART for classification. Building the tree. CART starts with the entire dataset and recursively splits it into subsets based on the values of input features. At each node, CART evaluates different splitting criteria such as Gini impurity or entropy to determine the best feature and threshold for splitting the data. This process continues until a stopping criterion is met, such as reaching a maximum tree depth or minimum number of samples per leaf. Making predictions. Once the tree is built, classification decisions are made by traversing down the tree from the root node to a leaf node. At each internal node, the algorithm evaluates the condition based on a feature and threshold and moves either left or right accordingly. The process continues until a leaf node is reached, which corresponds to the predicted class label for the input data. Coming to CART for regression, building the tree. Similar to classification, CART recursions the feature space based on binary splits. However, in regression, CART uses different splitting criteria, such as minimizing the mean squared error to determine the best feature and threshold for data, making regression predictions in a similar way to classification by traversing down the tree from the root node to a leaf node. At each internal node, the algorithm evaluates the condition based on a feature and threshold and moves either left or right accordingly. The process continues until a leaf node is reached, which contains the predicted numerical value for the input data. Gini index or impurity. Gini impurity is a measure of how often a randomly chosen element from the dataset would be incorrectly labeled if it was randomly labeled according to the distribution of labels in the subset. It ranges from 0 to 1, where 0 indicates perfect purity, all the elements belong to the same class, and 1 indicates maximum impurity, that is, elements are evenly distributed across all classes. CART model representation. A CART model is represented as a binary tree structure where each internal node represents a decision based on a feature and each leaf node represents a prediction. The tree structure is easy to interpret, allowing visualization of the decision process and feature importance. Now let us see how a CART algorithm works. CART algorithm works by iteratively partitioning the dataset into smaller subsets based on the values of features. At each step, it selects the feature and threshold that best splits the data, aiming to minimize the impurity or variance within each subset. This process is repeated recursively for each subset until a stopping criterion is reached. Once the tree is constructed, it can be used to make predictions on new data by traversing the tree from the root to a leaf node. The steps involved in working of a path algorithm include decision trees, binary recursive partitioning, splitting criteria, tree growing process, pruning, and prediction. Now, coming to the first, decision trees. The fundamental building block of CART is a decision tree, a hierarchical structure resembling an upside down tree. Each node represents a decision point based on a feature in the data. Branches stemming from a node represent possible outcomes of that decision, leading to further decision points or leaves at the end, signifying predictions. CART is a non parametric method, meaning it doesn't make any assumptions about the underlying distribution of the data. It's based on the concept of binary recursive partitioning, where the input space is split into smaller regions based on certain criteria. Now, coming to binary recursive partitioning, CART builds a binary tree structure where each node represents a partition of the input space. At each step of the partitioning process, CART selects the feature and split point that best separates the data into two child nodes, optimizing a specific criterion such as Gini impurity for classification or mean squared error for regression. Now, coming to splitting criteria. For classification tasks, CART uses impurity measures like Gini impurity or entropy to evaluate the homogeneity of a split. It selects the split that minimizes impurity. For regression tasks, CART uses measures like mean squared error to evaluate the homogeneity of a split. It selects the split that minimizes the error. Now, tree growing process. The tree starts with a single node that contains all the training data. At each iteration, CART selects the best split among all features and their possible values. The splitting process continues recursively until a stopping criterion is met, such as reaching a maximum tree depth, minimum number of samples per leaf node, or when no further improvement is in impurity or error reduction is possible. The next step is pruning. After the tree is fully grown, pruning techniques are applied to avoid overfitting. Pruning involves removing nodes from the tree that do not significantly improve predictive accuracy on a validation dataset. Now, coming to the last one, prediction. Once the tree is constructed, predictions are made by traversing the tree from the root node to a leaf node based on the input features. For classification tasks, the predicted class is usually the majority class of the instances in the leaf node. For regression tasks, the predicted value is typically the mean or median of the target variable in the leaf node. Now, how a decision tree cart is implemented. Cart implementations are available in various programming languages and libraries, including Python, with libraries like scikit-learn, R, and MATLAB. These implementations provide user-friendly interfaces for training and evaluating cart models. Now let us discuss about some advantages of cart algorithm. Interpretability. Cart produces decision trees that are easy to interpret and understand. Each split in the tree corresponds to a simple decision rule based on the input features, making it straightforward to explain the model's prediction to stakeholders and domain experts. Versatility. CART can handle both classification and regression tasks, making it a versatile algorithm suitable for a wide range of predictive modeling problems. Whether the goal is to classify data into discrete categories or predict continuous numerical values, CART can be applied effectively. Non-linear relationships. CAT is capable of capturing non-linear relationships between input features and a target variable. Unlike linear models, which assume a linear relationship between variables, CAT can automatically detect and model complex non-linear patterns in the data. Robustness. CAT is relatively robust to outliers and noisy data. Outliers may affect individuals in the train, but they are less likely to have a significant impact on the overall structure of the tree. This robustness makes cards suitable for datasets with noisy or imperfectly measured variables. Handling mixed data types. Cart can handle datasets with a mix of categorical and numerical features without requiring extensive pre-processing. It automatically selects the appropriate splitting criteria for each feature type, making it convenient for analyzing real-world datasets with diverse data types. Scalability. Cart is computationally efficient and can handle large datasets with thousands or even millions of observations and features. With optimized implementations and parallel processing capabilities, CART can effectively build decision trees for big data applications. Now, coming to the disadvantages of CART, uh, overfitting. One of the primary challenges with CART is the tendency to overfit the training data. Decision trees are prone to capturing noise and outliers in the data, leading to excessively complex models that perform well on the training set but generalize poorly to new unseen data. Overfitting can be mitigated using techniques like pruning, cross validation, and setting constraints on tree size. Next one, instability. CART models can be unstable, meaning small changes in their training data can result in significantly different trees. This sensitivity to data variations makes CART susceptible to high variance, especially when dealing with small or noisy datasets. Bias towards dominant classes. CART tends to favor splits that result in pure nodes with dominant class labels, leading to biased predictions in favor of the majority classes. This bias can be problematic for imbalanced datasets where one class is significantly more prevalent than others. Difficulty with continuous variables. While CART handles categorical variables well, it may struggle with continuous variables, especially if they contain many unique values. CART typically partitions continuous variables into intervals, and the choice of split points can significantly impact the resulting tree structure. Lack of global optimization. CART uses a greedy recursive partitioning algorithm to construct decision trees, which may not always lead to globally optimal trees. The algorithm makes locally optimal decisions at each split without considering the overall structure of the tree. As a result, CART may not always find the most efficient or accurate tree configuration for the given data. Limited representation. Despite their flexibility, decision trees have limited representational power compared to more complex models like neural networks or gradient boosting machines. They may struggle to capture highly intricate relationships or interactions between variables present in the data, especially when dealing with high dimensional or non-linear datasets. Sensitive to input features. The performance of cart can be heavily influenced by the choice of input features and their representation. Certain types of features may have a disproportionate impact on the tree structure, leading it to the biased or suboptimal models. Feature engineering and selection techniques are essential for maximizing cart's effectiveness. Now let us move to the applications of cart. Cart is used in various fields. Some of them include medical diagnosis. CART models are used in healthcare for diagnosing diseases based on patient symptoms, medical history, and diagnostic test results. They assist healthcare professionals in predicting the likelihood of different medical conditions, guiding treatment decisions, and identifying risk factors for diseases. Marketing and customer segmentation. In marketing, CART models help business segment customers based on demographic, behavioral, and transactional data. These models enable targeted marketing campaigns, personalized product recommendations, and customer retention strategies by identifying customer segments with similar characteristics and preferences. Fraud detection. CART models play a crucial role in fraud detection and prevention across various industries, including banking, insurance, and e commerce. By analyzing transactional data and user behavior patterns, these models identify anomalous activities indicative of fraudulent behavior such as unauthorized access, identity theft, and payment fraud. Predictive maintenance. In manufacturing and industrial settings, CART models are employed for predictive maintenance to anticipate equipment failures and optimize maintenance schedules. By analyzing sensor data, equipment usage, and historical maintenance records, these models predict when machinery is likely to malfunction or require servicing, minimizing downtime and maintenance costs. Environmental modeling. CART models are used in environmental science and ecology for predicting ecological phenomena, species distribution, and environmental risks. These models analyze environmental variables such as temperature, precipitation, soil composition, and habitat characteristics to forecast changes in ecosystems, biodiversity loss, and the impact of climate change. Market research. CART models assist market researchers in analyzing survey data, consumer preferences, and product feedback to gain insights into market trends, consumer behavior, and brand perception. These models identify key drivers influencing consumer purchase decisions, market segmentation strategies, and opportunities for product innovation and differentiation. Now, finally, in conclusion, CART is a versatile algorithm for building decision trees that can be used for both classification and regression tasks. It offers a balance between interpretability and predictive performance, making it a valuable tool in machine learning and data analysis. Despite its limitations, CART remains a popular choice for solving a wide range of real world problems. Thank you.